Did you know that there are 6 different ways to find the area of a triangle? Let's explore. But first, if you haven't checked out the previous video on angle chasing, there's many cool and interesting problems, and they're the fundamentals for what we'll be looking at today. So let's start off with the most basic formula, which most of you are probably familiar with. Half base times height, which is the area of a triangle, where this is the base and this is the height. Now, there are many other different formulas to calculate the area of a triangle, because not always you're going to have the base and the height. Sometimes you might have 3 side lengths of a triangle. You might have, we're given that there's 3 sides of a triangle are A, B, and C. Then you can use Heron's formula to calculate the area of a triangle. So basically, Heron's formula states that the area of a triangle is the square root of s times s minus a times s minus b times s minus c. So what is s? Well, s is the semi-perimeter. So a plus b plus c divided by 2, that is the value of s, half of the perimeter. So to use Heron's formula, you just take s itself and then multiply it by s minus each of the sides, a, b, and c. And then you take the square root. It's very useful when you have 3 sides of a triangle because you're not given the height necessarily. And there's another way to find the area of the triangle using incenters. The incenter of a triangle is the intersection of all of its angle bisectors. This point is basically the center of the inscribed circle. So over here you can see that this Inradius is r. So the Inradius, there are different formulas you can use to find the area in terms of the Inradius. The area of a triangle is the Inradius times the semi-perimeter. And why is this true? Well, the cool thing here is if you break up this triangle into 3 pieces with side lengths A, B, and C, well, guess what? Using our standard half AB formula, half base times height formula, we have the area of this triangle is half CR. We have the area of this triangle is half AR, and the area of this triangle is half BR. So the overall area is half times A plus B plus C times R. And that's why it's radius in radius times semi-perimeter. Isn't that cool? So now we discussed 3 ways to find the area of a triangle. Okay, but we're still not done. There's still many more ways left. Also, by the way, another cool fact is that the Inradius of a right triangle, which we'll discuss more next video, is half of A plus B minus C, where A and B are the legs of the triangle and C is the hypotenuse. Okay, so now there's another way to find the area of a triangle using circumcenters and circumradius. So essentially, the circumcenter of a triangle is the center of the circumscribed circle. So if we draw a circle around the triangle such that the circle passes through all 3 points of the triangle, the circumcenter is the center of that circle, and the circumradius is the radius of that circumcircle. So using the circumradius, the area of a triangle is ABC over 4R. So over there you can see that if you're given 3 sides of a triangle, A, B, and C, and we're given the circumradius, we can find the area, ABC divided by 4R. Also, you can do backtracking here. If you know the area, you can find the circumradius from this, and this is sometimes useful. So here's another cool theorem, Shoelace theorem. So Shoelace theorem essentially allows you to find the area of a triangle using coordinates. But we'll discuss more of this in the coordinate geometry video. And Pick's theorem as well, we'll discuss more in the coordinate geometry video, but they're useful for finding areas when you have lattice points, etc. Now let's take a look at a cool example problem from the AIME. As shown in the figure, triangle ABC is divided into 6 congruent triangles, as shown in the figure below, by lines drawn from the vertices through a common interior point. So they're all drawn through this common interior point right here. The area of 4 of the triangles are as indicated. Find the area of ABC, which is the big triangle. So we know the area of 4 triangles. How do we find the area of the whole triangle? Well, to find the area of the whole triangle, what we need to do is somehow find the other 2 areas that we don't know. But what are these areas? Let's call them A and B. We don't know what they are, so let's just give them a variable. They'll be easier to deal with. So now we have to somehow find what A and B are using the other areas we have. 84, 40, 30, 35. How do we use that to find the area of 84? Well, the key thing here is that what we can do is drop an altitude right here. So the key thing is that this altitude h, this altitude is shared between this triangle and this triangle, which have areas of 30 and 40 respectively. So what's cool is now, let's say this is A and this is B. Well, now we know that 40 is equal to half BH. Or let's just call it X and Y instead, because we already used A and B. So 40 equal to half XH, right? And 30 is half YH. So now what we can do from here is see that because we have 40 is half XH, 30 is 1/2 YH, let's divide the first equation by the second equation. Doing this, we get 4/3 equal to, well, the 1/2s and h's cancel, x over y. Aha! Now we know the ratio of x to y is 4/3. So how can we use this information? After all, we're chasing areas, not lengths. So the key thing here is now, let's drop another altitude. Drop one all the way there, over there. This is now h of the big triangle. Let's call it big H, capital H right there. So if this is the height of the big triangle, then, well, we know the areas, the ratios of x to y. So what is the area of this triangle here? Well, that's just going to be 1/2 big H x. And the area of this triangle over here is 1/2 big H and y. So, well, we know the area, the ratios of x to y. So, therefore, the ratio of 1/2 big Hx to 1/2 big Hy is just the ratio of x to y, which is 4/3. Well, what is 1/2 big H in terms of the variables a and b and maybe some of the other numbers that we know? 1/2 big Hx is nothing but 84 plus b plus 40, because those are the 3 triangles, small triangles, that make up this triangle. So 1/2 big H is 40 plus 84 plus b. What about 1/2 big Y, big HY? That's this triangle over here. It's made up of 3 pieces: the 30 one, the 35 one, and the A one, Remember we defined that earlier. So that's going to be 65 plus a. And 1/2 big hx is 124 plus b. So now from here, we know that 124 plus b divided by 65 plus a. Remember, this was just 1/2 big H, this triangle here, right? And this one here, 65 plus a, is this triangle here. And the ratio of x to y is 4/3. So that's also the ratio of the areas 4 to 3. So, well, we have two variables in only one equation. So that's clearly not enough to solve the problem. But we've done it once and it gave us some information. Can we do it again maybe, but instead use different areas instead? Okay, so the key here is now what we can do is use the other sides of the triangle instead of the bottom two that we used earlier. So we had this is A, this is B. What we can do now is see that the ratio of the areas of this triangle to this triangle is 35 over A. And we can again drop some kind of altitude. Let's call it maybe I. So if that altitude is I, then we know that the area of this triangle is just 1/2 base times I, and the area of this triangle is 1/2 of this base times I. So the key thing here is that 35 over A, because they have the same altitude, just like earlier, is the ratio of this base to this base. Let's call them J and K. J and K. This is equal to J over K. So if that's equal to J over K, well, just like earlier, we can make another big altitude. Let's draw over there. So the key thing here is that if we're looking at the ratio of this area to this area here, well, the key thing is that they also share an altitude, this big altitude here. So the ratio of those areas, because the altitudes are the same, is the ratio of the bases. So J over K is also equal to the ratio of this triangle, the green one, divided by the orange one. The area of the green triangle is equal to 35 plus 30 plus 40, 105. The area of the orange triangle, 84 plus A plus B. And this J over K here doesn't really matter because now we've already found it in terms of A and B. And now, guess what? We've got two variables and two equations. So now we can try solving for each of those variables. 372 plus 3b is 260 plus 4a. 112 plus 3b is 4a, right? Let's expand the second equation. We have 35 times 84 plus 35a plus 35b equals 105a. You can subtract 35a from both sides to get, and we'll end up with 70a on the right side and 0a on the left side. And now we can divide by 35 from the second equation to get 84 plus b equals 2a. And this seems pretty simple. So what we can do is now substitute. B is 2a minus 84. So 112 plus 3b, 2a minus 84, is 4a. I guess this is just 112 plus 6a minus 3 times 84, that's 252, equal to, for A, 2A equals 252 minus 112 equal to 140. So A is 70, and from here we solve B to get that B is 140 minus 84, which is 40 plus 16, 56. So A is 70, B is 56. And just like that, now it's an addition problem. Or is it? Well, you can add them all up, but that will definitely work. But another cool shortcut, the sum of these three areas is 40 plus 30 plus 35. So the area of this region over here is 105. And earlier, just like we found, because this triangle has the area of 35 and this one 70, the ratio of their bases is 1 to 2. So that means if the area of the green triangle is 105, because the overall base will be 3 times bigger, because this base is 2 times of this section, then the overall base will be 3 times this section. So the area of the whole triangle will just be 3 times 105, 315. And that is the answer. Let's recap. Basically what we did is we assigned variables A and B. Then we used the very cool property that if they share the altitude, then the ratio of the areas is just the ratio of the bases. And then we constructed a 2-variable equation from there and easily solved and found our answer. Let's take a look at another cool example. 3 congruent isosceles triangles are constructed with their bases on the side of an equilateral triangle of side 1. Okay, let's see. We have an equilateral triangle, side length 1, 1, 1, 1. Or maybe let's write that on the inside, because we're going to be putting isosceles triangles on the outside. 3 congruent isosceles triangles are constructed on this base. So maybe something like this, something like this. Okay. So we're given that the sum of the areas of the 3 isosceles triangles is the same as the area of the equilateral triangle. What is the length of one of the 2 congruent sides of the isosceles triangles? So what we should do is see that because the sum of those 3 isosceles triangles is the equilateral triangle, well, a cool trick you can see is that let's draw the center of the equilateral triangle. Well, the key thing here is that we can divide this equilateral triangle into 3 triangles. There are actually many ways to proceed from here, but let me show you one cool, simple solution that has a very unique flavor to it. Essentially, we're given that the sum of those 3 isosceles triangles equals the equilateral triangle. Well, what does that mean? Well, because we broke this equilateral triangle into 3 parts, each of those 3 parts must be equal to one of the isosceles triangles. So what that means is this triangle here, the area inside here, must be equal to the area inside this one right here. Similarly, the area inside this one must be equal to the area inside this one. And similarly for the last one, the area inside that triangle must be the area inside this triangle. The reason is because if those triangles are equal, then each of them has 3 parts. There's 3 isosceles triangles, and there's 3 parts in the equilateral triangle. Another way of thinking about it is you can think about folding each of those 3 triangles in so that there's no overlap. and that it encompasses the full equilateral triangle. And if we do that, we would actually see that it's the same thing. The area of one of these triangles is the same as the area of this triangle if we fold it in, because it's kind of like two layers, one from the isosceles triangles and one from the base equilateral triangle. But we're asked to find the length of one of the congruent sides of the isosceles triangle. This one. Or this one, let's say. So, how do we use this fact that the equilateral triangle has side length 1 to find this isosceles part over here? Well, the cool thing you can actually see is that these two triangles are congruent to each other. Those triangles are congruent to each other because, well, they have the same area, they have the same base, and so they have the same height. And they're both isosceles triangles. And also, we can, if we fold it inwards, we would see that this side right here would correspond with this side, and this side over here would correspond with this side if we folded it in. So then we could see that one of these congruent sides of the isosceles triangle would just be one of these distances over there. One of those distances over there. Well, how would we find one of those distances over there? Well, the key thing that we can use here is that the median, we can actually extend this out to form the median. And then we could see that this median would be the total length from the point to the midpoint. So median is the segment connecting the point to the midpoint of the other side. So that would be the median. And a cool property of equilateral triangles is that this distance from the point to the centroid is 2/3 of the median. So if this distance is 2/3 of the whole median, then we can see that all we have to do is find this distance, and we would find that distance to the centroid. And the centroid is the intersection of the three medians to the opposite sides. So how do we find this median distance? Well, as it turns out, for an equilateral triangle, the median is the same thing as the altitude, and so on. So, to find the altitude of the equilateral triangle, we'll actually cover this more in the next video, but it's a cool property that it's just square root 3/2 times the side length, which in this case is 1. So square root 3/2 will be the altitude. And this distance will be 2/3 of that. Square root 3/2 times 2/3 to get this distance over here, which is equivalent to one of our congruent sides of the isosceles triangle. Cancel out, we get square root 3/3. That's the answer for this problem. Okay, so we already discussed some of these triangle properties. A median is a line connecting a point to the midpoint. Like this is a median connecting to the midpoint. And a centroid is the intersection of the three medians. And the centroid is on the median, and it's 2/3 of the way up from one of the vertices to the midpoint of the opposite side, like we discussed in the previous problem. We use the fact that this whole centroid, this distance to the centroid was 2/3 of the entire median. And that's always useful, even when it's not an equilateral triangle. So that's cool. Let's solve another problem that uses these properties. In triangle ABC, we have side length AB equals 12. So AB is 12. Let's draw a triangle. So we can label them A, B, C. That's a triangle over there. And AB is 12. BC is 24. and AC is 18. Okay, the line through the incenter of ABC parallel to BC intersects AB at M and AC at N. What is the perimeter of AMN? Incenter of ABC. So like we discussed earlier, the incenter of a triangle is just the center of the inscribed circle. So I'm going to draw an inscribed circle, a very perfect circle, as you can see here, using my circle drawing tool that I have, that you probably won't have. So this is the incenter, this is R, this is R, this is R, but maybe we don't really need the radiuses for this problem. The line through the incenter of ABC parallel to BC intersects BC at AB and at M and AC at N. There's a line through the incenter parallel to BC. Let's draw it. Maybe it will be something like this. Something like this. Yeah, that's a line parallel to the parallel to BC through the incenter. It intersects AB at M and AC at N. We're asked to find the perimeter of AMN. How are we supposed to do this? Well, they're parallel. What does that mean, really? Does it give us any useful information? AMN. Well, what is incenter? Is incenter just a circle, or is there another property? Oh yeah, right. There's angle bisectors too, isn't there? There's angle bisectors. So all the lines passing through the incenter form angle bisectors. Let's say they form angles of A and A here, B and B here, and C and C here. Okay, well, we still we don't know what to do to find AMN because we have no idea what MN is. Well, we need to somehow use the parallel line condition. A good strategy in problems, especially geometry, is to look for information we haven't used. Parallel lines. We've used incenter condition. How do we use the parallel line condition? Well, you might remember angle chasing formulas. There's corresponding angles. This angle is equal to that angle. So that must be 2b. And similarly, this angle equals this angle, 2c. Okay, that's cool, but that's not the only condition parallel lines give us. There's also another condition here. Look how we kind of have a transversal here through two parallel lines, and you can see the alternating interior angles. So it's kind of like this alternating interior, and those two angles are always equal. That's a property for parallel lines. Therefore, that must be B as well. And similarly, by alternating interior angles, this angle equals this angle, C. But now, B, B, C, C. Those are just isosceles triangles. And what do we know about isosceles triangles? Well, if the two base angles are equal, the base sides will be equal as well. So that means that this side length is that, and this is, maybe let me draw with a different color. This side length is, and then as you can see here, this is equal to this, and this is equal to this by those angles that are equal. But we still need to find the perimeter of AMN. How do we know what AM is? We don't know what AM is. We don't know what MN is either. But the thing is, we don't need to know what AM and MN or NA need to be. Because you can think about it, let's say we have this perimeter in green. Let's say we have that perimeter in green. We've got three parts: AM, AN, and then the bottom side. So because this length here is equal to this length here, we can move that over there. Let's just completely erase that and make that there. It's still the same length because this length equals that length. So instead of writing AM plus this piece here, it's just AB. And similarly, this piece over here, because we've had those green parts are equal, this is equal to that. Instead of we can just write this length here instead of this length here. So now instead of AM plus MN plus NA, we move some parts around. We move this part here and this part here. Just get AB plus AC, which is equivalent to the perimeter. And AB plus AC is just 30, our answer. A really cool problem, isn't it? Basically, what we had to do was we saw the angle bisector condition first, did a little bit of angle chasing, which we learned in the previous video, using parallel lines and isosceles triangles to find out the lengths were equal. And then after that, AM plus MN plus NA, we moved this part here and this part here. So then the perimeter was just AB plus AC. It's a really clever application of angle chasing and the incenter properties. Now there's many practice problems you can get in the free book, Mastering AMC 1012. It contains most of the important concepts you need to know to do well on the AMCs. Free link, you can click on the description to start using it today. So next off, we're going to discuss special triangles. We already did an overview of triangles, but there's special triangles like equilateral triangles, right triangles, and more specifically 45, 45, 90, 30, 60, 90 triangles. And their applications can be used in even the most complex theming problems. We'll explore all of that over here.